Okay, so let's get started. Back to our integration by parts stuff. I wanted to show, we had, who was not here last time we were in here, which was yesterday during Flex? Just Marcus? And you, right, that's right. I knew somebody else was missing. All right, so let's get back to integration by parts. All right, so integration by parts, part 2. Revenge of the integrand. No. All right, so if we have a function, let's say first of all, you can recognize integration by parts when you see it because you have a product under the integrand. Okay? You have a function and another function. So we have to go back and choose one of my objects to be taken a derivative of, another object to be taken an integral of. And that's this box that we went through. So one thing is going to go in this corner, one thing is going to go in this corner. We're going to take a derivative here, and we're going to integrate there. Now, choosing which one is sometimes the trick. If you choose a particular thing to go in a box to take a derivative of, or put something in a box and take an integral of it, and it looks worse than what you started with, you might want to consider just going back and reversing it and putting them back in each other's places. So for example, if I incorrectly chose sine x to go here and x to go there, this is wrong. I want this. And here's what's going to happen. The derivative of sine is cosine. And now I've got x squared over 2. So now this would become, excuse me, remember how we choose this, these and then those. I'm going to make my function worse. And now you might want to say to yourself, this is not a good idea, okay? Unless there's a really good reason why you need to make it more ugly, which we saw yesterday with the example of natural log. And I'll do that example just for giggles. So doing this a different way, now everything is going to come out a little bit nicer. Okay, so choosing what goes in what box is, that takes a little bit of practice. But generally speaking, you're looking to get rid of something. Okay. And just to complete this, to make sure that I've got it correctly, if I take a derivative of that, I had better get what is inside the integrand to check myself. So, to check, all right. So I have to use the product rule. And so it does work. All right. Now, I showed you guys that if you are in the situation where one of your terms cycles, like a trig function cycles, sines and cosines are nice that way, or if you have an exponential, those cycle consistently also. There's a nice table that you can put your stuff in. So let's do one of those. Okay. So you should recognize that the x squared is going to eventually, after repeated integration by parts, doing this thing over and over and over again, will eventually get destroyed. And I have something that cycles as well. So I'm going to go ahead and do this one long form. You don't have to write this down because it's in the notes, and we're going to use the table in a minute to get the answer anyway. But I want to show that doing it the long form and by table form, we get the same answer. Okay? So the table is a trick. It's a beautiful, nice, happy little trick, but I want to show an example, at least one, of why or what it actually does. So x squared 2x e to the 2x. What goes here? Right, 1/2. Right, exactly. The other way, if repeated derivatives would every time I took a derivative, it would spit out a 2. But every time I integrate, it's going to spit out a 1/2. All right, good. Well, you would have seen it. Okay, so now I have and the integral of x e to the 2x. The 1/2 and the 2 just killed each other off. Okay? Yeah, the 1/2 and the 2. And you can recognize that again, I have to do it again. So one more time to play with. So x1 e to the 2x 1/2 e to the 2x. It almost looks like it, right? Because normally there should be another one. You would think there would be another 1/2 out in the front. But because I had x squared, that one happened to die off. Think about what would happen if I had x cubed. There would be a 3 in there and a 1/2 in there, right? And now finally, and this is going to become 1/4 e to the 2x, and that's a plus. So a couple of things to notice. We have this progression that happens. We have sign changes that occur. So let's do this one by the table. If we get it right, we're good to go. So in this column, something is going to be taken a derivative of. In this column, something is going to be integrated repeatedly. And in the last column, I'm going to toggle between a plus and a minus. So this is x squared, 2x, 2. So I'm repeatedly taking derivatives at each step along this column. E to the 2x. Now, every time I take that integral, we have to keep track of that coefficient that's going to be coming out. definitely one step longer. Marcus, you'll see in a minute. Mm-hmm. That's why I stopped recording. And that's how we read off the table. We go in a diagonal fashion. Okay, so it's important. Please don't make the mistake of starting off with a negative sign here. That would definitely screw everything up on the road. Okay. And now we just complete it all. So we have x squared e to the 2x all over 2 minus 2x. Oh. Looks like we lost something here, didn't we? Yeah.
Plus one that you started with, that just tells you the sign of the first sort of term, right? It doesn't
Yeah. No. You're multiplying everything in the red oval together.
Okay, so yeah, that's fine.
Yeah. So it's all three of those things multiplied together. Do you see how it's built? Yeah, you just multiply. You multiply this, this, and this together. That's your first term.
Right, but on the table, how do you...
It's a pattern of repeated, yeah, because like, for example, if you'll notice, when I do this, I get alternating signs because I have to distribute this negative at each repeated integration by parts. I'm producing a negative sign in between two terms, here and here. And since it's nested, they get distributed, and then every other one winds up being changed. Now, that is not to say that you couldn't, that when I do, it also spits out positive and negative signs. Okay, like for example, if I had in there, okay, repeated derivatives or repeated integrals over and over and over again, you're going to be spitting out negative signs because, the derivative of cosine is negative sine. So eventually it'll be spitting out negatives too. So there might be some sign changes going on in there. Okay. Okay, so repeated cyclic integration by parts has this nice technique. But what would happen if they both cycled? Just give up. Right, exactly. Say, waiter, check please, I'm done. Well, let's see what happens. Well, obviously the table is going to be a problem, right? Because my left-hand column is not going to go away. I'm going to wind up just getting the same things out all the time, right? Okay, so let's just see what happens. What do you want to pick for your U? What goes up here? You want to pick the sign? Sure. du. Okay, what's my dv going to be? Obviously, there's only one thing left. Right? Okay. This is not fruitless, believe it or not. We're all good? Why don't you do the next one? The next integration by parts. We should. It's not fruitless. I am not walking you down a blind alley. Trust factor is out the door. It's like I would never lead you down a blind alley unless it led to a lion's den. Right. Logic wheels are spinning. Right. Everything I say is a lie. Which means I'm not lying. TOK all over again, right? Mm-hmm. Epistemology. Take a minute. Is that what everyone got? What's wrong? Now I'm just going to clean it up a little bit. There's a beautiful thing about to happen. Okay, does everyone agree with all of that? Yep. You know, I'm just distributing and cleaning up and, you know, dusting it down a little bit. But,
I know what you did, but I can't like make my
line do it too. Like,
Well,
so I did the,
This is this for this, or this is for this, and this is for this.
yes. So there was,
Okay. So now this times this minus the integral of that times that. New line. Don't forget the dx. So
no, no, I already did that.
no, that was this.
Yeah.
Oh no, okay.
I was still working.
Oh yeah, there's two terms. See your pencil.
I have this one, but it's still at the back.
This integral is
Okay.
that is equal to those two terms. This is equal to those two terms.
Okay.
Okay. So now here's something really interesting. We got the same thing back. We kind of expected that because we knew we had a cycle, right? The simplest magic trick. Whatever the heck that integral is, okay, whatever it is, let's just call it something. I for integral. So I, whatever I is equal to all of this. See how that works? That's really cool, though. And now, oh, you're back. Now, the gang's all here. Hey, guys. Would you miss this? What else? All right, so, okay, guys, pull out your notes and get caught up quick. All right. So, really quickly, what have we done in the last 20 minutes? When you have a function that where both functions cycle, you will do integration by parts until you come back with the same integral again. Okay, so take a few minutes, you two, three. Learning. I recorded this lesson, by the way. This episode has been recorded under a live studio audience. No, I was going to keep it all to myself. And right. We'll play them at holidays. Right, no, just kidding. Right, and family reunions. No, yeah, I'll post it up soon. Okay. So here we are. I know, we have repeated integration by parts, but look. So we are repeatedly integrating by parts, and since both functions cycle, cosine, trig, and exponentials both cycle, we wind up getting the same thing back from whence we came, right? And now you do a really sneaky trick. Combining like terms. So you get 5/4 I, and then we get rid of the fraction. And of course, you can distribute the 4/5 and clean stuff up a little bit. That all works. But that's the whole idea. This? Right there? Yeah, I can see Pat. But sometimes stuff up. Just looking at this, the only thing the distribution is going to do is change this to a 2/5 and that to a 1/5. And that's all. So that's not really doing a heck of a lot. But in theory, there could be some things that, eliminate a radical or something. Hint, hint. Huh? Because I still have a constant. There's still a constant of integration that's being thrown in here. I picked a letter, man. I had 26 to choose. Yeah. Well, we're going to go to the boards in a minute. Okay. Huh? Sigma notation all the time. And you know what? We could go to Cyrillic letters, Hebrew letters. Yeah.
Or we could go to Greek letters.
You hang around enough Russians, you pick up a few things in Russian. They call it. His name was Saint Kirill. Yeah. All right. So hit the boards. I'm going to pause this episode of the Ronco Show. We'll be back after a brief word from our sponsor.
Who's our sponsor?
The letter I. All right, ladies and gentlemen. So yeah, we worked this crazy integral. Turned into this big steaming pile of math. All right, so. All right, there's one thing we don't have a heck of a lot of time left, but there's one tiny little thing I want to talk to you about when it comes to definite integration. Oh, no.
Are we using the board still? Or no?
Sure. What if I gave you
Wait, is
this?
this a new concept?
Sort of.
Okay, then okay.
Yeah. Yeah, so like open model.
Oh, great.
All right, so how does one do integration with piecewise functions?
Neither cherry.
So, not in any realistic way. Guys, please. Thanks. So, what are we doing here? Let's take a look at it. We have two lines. So, what are we playing with? If we were to graph this, I'm just going to for things less than -1, we have that graph. So that graph looks like this, roughly speaking. Okay, positive slope of 1/2, negative y-intercept, but it only lives from negative infinity to -1. When we get to -1, okay, no, it's included, so it's a solid dot. Okay. The other function, which only lives from objects greater than -1, looks like this. right? Positive slope of 1, negative 1 intercept. It does not include that value. Okay? All right. Magic. It's the problem.
No.
Hmm? What's the question?
Okay, okay.
So we have a piecewise function that we are trying to integrate, and we're going to integrate it from -4 to 2. I'm eyeballing my graph. I'm not trying to make it accurate. The fact of the matter is that this is roughly speaking what this piecewise function looks like. So what we're doing is we're trying to find the area like that. Trying to find that red crazy area. Okay. So what do you think we got to do? Absolutely. We have to split this sucker up into different integrals. Okay? So from -4 up to -1, it looks perfectly normal with that function, the upper of the two piecewise functions. So we're going to split this up into -4 to -1. And then from -1 up to 2, it behaves like the other function. And now it's very straightforward. Yes?
There's oh wait, never mind. So there's the discontinuity and then there's the point.
Yeah, what about it?
Yeah, that's what I forgot that there was the actual point there. I was like, well, what if it's a discontinuity? Like, what would it have found?
It would still, now if there was a discontinuity at that point,
That's what I forgot.
right. So like for example, if at -1 it caused one of my functions to say have well, an asymptote would lead me to not being able to integrate it. But if it was like say the square root of -1 underneath or something like that, or a non-real answer, I'd have to see an example. But yeah, you might be able. Yeah. You would set the bound equal to b and then take the limit. Yeah. And of course, we can integrate this. This is nothing very exciting. But I wanted you to see piecewise functions being dealt with. Okay? Good. So now, how about this one? Absolute value now. Well, small rainforest. So, in this kind of a situation, the absolute value function does not have a straight integral. Okay, it's not one of our normal forms. If you think about it, taking the derivative of something and having an absolute value spit out by it all by itself kind of really doesn't make a lot of sense. So what we have to do when we play this game is realize what it looks like. So x squared plus x. What the heck does that look like? Yeah. Standard looking parabola. Here's why. You can graph it, but let's also see that because 0 is where it's going to flip, right? I mean, anything that's below, that's negative, is going to become a positive, right? That's what the absolute value does. So those are its two roots. Looks something like that, but that's really horrible. But the reason why I did it, yeah, I get it, but that's what the function really looks like. If you pull out a graphing calculator and graph the absolute value of x squared plus x, that's what he looks like. It looks that's what it looks like. So anything that was below the x-axis is now above the x-axis.
A little bit, yeah. Of what you had. I can see it with the hat though. Yeah.
Okay, Sven. Let's. All right. All right. All right. Let's go slay Gilgamesh, or whatever. No, whatever the hell there was. The other one. Grendel. Right. Grendel. Everyone likes Grendel. She's fun at parties.
Grendel's a guy.
That too.
Grendel's a monster that eats people.
Hey man, apparently that's like totally cool in some places. So this is how you graph this, guys. So now to do this, we have to break the integral up at every point where we have where we have a reflection. Okay. And this is at 1 and 0. So from -2 to 1. Okay, that's going to deal with this region right there. Okay, that's my first integral. This is my second integral, and that's my third integral. Yeah. Yeah, I'm sorry, you're right. Okay. Now, to get the integral of the middle region, we have to deal with the fact that our function is now upside down. So what are we going to do? Well, this area, whatever area that is, this region, it's a finite amount of space, right? And if my function were right side up again, this would be down below, right? Yeah, it would be down below. It would be negative, but now we just want it to be positive again. Well,
Just find the area and switch the sign.
you can switch the sign, you can switch the bounds.
Let's just switch.
It doesn't matter, yeah.
That sounds nice.
So that's region 2. And then finally region 3. I did, I switched the sign out. I just pulled the sign out. The absolute value just makes everybody positive. So the region from -1 to 0 is normally a negative area, right? So I flipped the sign on it and made it a positive area.
Oh, okay. It just tricked me off to a negative.
Yeah, yeah. Because that middle integral is going to wind up ending up being a negative number. And now it'll become a positive number. Okay. Does that all make sense? Good. All right. Okay. Yeah. I'm sorry, what? Yeah, I know. Okay, so ladies and gentlemen, there's some stuff here. These aren't so bad. These are small integrals. It's all integration by parts except for the last 4. You might be able to use integration by parts on the last 4, but you probably don't need. Oh, I'm sorry.
We're doing an immersion?
This episode of the Ronco Show has been brought to you by the absolute value of the integral I. Later, Marcus.